A rigid body of mass 0.3 kg is taken up slowly up an inclined plane of 10 meters at a height of 5 meters, assuming the applied force to be parallel to the inclined plane. Right? That's a good set of information. Slowly up and so on and so forth. Then they're then allowed to slide down to the bottom again. Okay. The coefficient of friction between the body and the plane is this. G is this. Find the work done by gravity. Okay. First thing is diagram. I mean, this is a bit complicated. So before we do anything else, we need to figure out a diagram. So if I have this as the, something like this. Seeing that's half, looks like half. Anyways, doesn't matter. So this is 10 meter length and this is 5 meter high. And the coefficient of friction is 0.15. Kinetic friction that is. So the object is taken from this point. Okay, then what else? I think we can start with this. So we are pulling it up. Then obviously gravity is pulling it down. And this is 0.3 into 10. And yeah, we have normal force. And we have friction also. Because there's coefficient of friction, there is frictional force as well. And this is normal force. Okay. So these are all it. And we have 9.8 meter per second square. Things getting pulled down. That's it, I guess. Yeah. So many Newton. Okay. So this is the entirety. And we need the free body diagram actually. That is pretty much needed. So we have the force to the right. Then we have the normal force. Then we have a component downwards. And we have this and we have this. Quite a few things. So this is the force that I apply. This is a normal force. This is a component parallel, the weight component perpendicular to the slope, and this is parallel to the slope. This is F of friction, and this also we need to figure out. Okay, so let's do it off. So for that, we need to figure out theta, and then this will be related to theta over here, and then I'll be able to figure out this. Okay, so let's figure out theta. So calculating theta. So we have sine theta is equal to opposite by hypotenuse. So that's half. And so theta is how much, guys? Therefore, theta is 30 degree. So since this is 30 degree, this will be 30 degree, and down will be, right, 3. So 1.5 root 3 Newton. And this is 1.5 Newton. And this is normal force. So let me change it to R as a reaction force. If not, it's confusing. So this also will be 1.5 root 3 Newton. Frictional force will be this times of 1.5. So 1.5 root 3 times of 0.15. So many Newton. So quite a few things happening over here. Okay, so that is that. So I'm not going to talk about resolving weight. So you guys have to complete this part. I already showed it. And then also the frictional force. So all of this is something that you guys have to know by now. So frictional force, I'll help you guys a bit. So we have mu K times of your normal or reaction force in this case. Okay, first question. So what is the work done by gravity? What is the work done by gravity? Force over the round trip. See, anything that goes up and comes down, what is it? The displacement will be 0. So as the displacement is 0, around the trip, the work by gravity is 0. That's it. Simple and straightforward. Now let's move on to the next one. The work done by applied force over the upward journey. So there's no actual value given, but the clue is over here. Even I was stuck a bit initially. I reread the question. They given the clue as slowly up. So for something to be slowly up, so we have and up as positive direction. So applying Newton's second law along the slope. So along the slope, what we have? Force F. If I have not done any silly mistake, then 1.5 minus 0.15 times of 1.5 root 3. All of this should be approximately equal to 0. Reason being, because object is moving slowly up. That's the only clue that we have. So we can assume the acceleration to be approximately 0. Acceleration to be approximately 0 meter per second square. Okay, guys. That's an assumption that we have to make. Okay, for here, I don't have an option, guys. I'm using calculator. Into 1.5 times of root of 3. Sorry. And this is 1.889. So 1.89. 1.9 also, it's okay. Approximately 1.9. Let's suppose that we are applying. So, sorry, I don't know. Just a second. Okay, with this as the force, then the work, therefore the work is equal to force times of displacement times of cos theta. Here theta is 0 as force and displacement. Force is along the is parallel to slope. So this is nothing but 1.9 times of 10. So approximately, everything is approximate actually, 19 joules. Okay, guys. So yeah, right? Okay. Oh, I made a silly mistake. I took G as 10, by the way. I knew that I did something. I'm taking G as 10. My bad. Take G as 10 and you will get my value. If not, if you want to take 9.8, take 9.8 and everything else remains the same. Okay, work done by frictional force over the round trip. For frictional force, things are not as gravity. Sorry, I have not made it clear why this is 0 to a large extent. So this is to be taught, later topic. Okay, yes. So I'm not able to clear it now. So we'll understand this in the next section. For now, you guys can take that as 0. While the work done by frictional force around the trip is non-zero. Okay. So it has to do with conservative nature of gravity, while this is not conservative in nature, the friction that is. So friction work. So friction, what it does is friction always it opposes motion. So it does negative work. No, actually opposes motion. Actually, this is not the reason. Sorry. Just a second. So work done by friction will be minus f of x into 2 times of the slope length. So this will be how much, guys? This is I think calculate, right? Yeah. 0.15 times of 1.5 times of root of 3. So we have it to be 0.39, 0.4 honestly, approximately. So 0.4 approximately times of 2 times of slope length is 10. All of this is possible because friction is non-conservative. As friction is non-conservative in nature, so we have to not consider all this, around the trip and all of that. We just have to consider where did you go, where did you come back. So all of this is approximately equal to 48 minus 80. Wait, what? No, sorry, 8 joules. It can't be more than this, right? Okay, that's that. And finally, we have kinetic energy of the body at the end of the trip. So if I leave it from the top, what is the kinetic energy at the end? So there are different ways of doing it. Honestly, there are many ways of doing this. I'm going to go a bit lazy and I'll figure out the answer in a much easier manner. See, the point is we have to figure out the energy of the object when it comes down. Okay. So this particular object has some potential energy over here, and that is equal to mgh. And that will be equal to the kinetic energy at the bottom, provided we have a frictionless surface. Because friction is there, there's work that has to be done against friction, that energy will be taken out. So if I subtract this value from the frictional force, so that is already calculated for going and coming. So half of that will be 4 and you're pretty much done. Right? So let me explain this. Kinetic energy at the bottom will be equal to potential energy at the top minus energy lost. If you are not understanding this part, you will understand with the next section. Lost due to friction. Actually, we read one statement, it comes over there, about work energy theorem. Again, all of this will add up in time. So this is equal to m into g into h minus 4 joules, half of this. So mass is how much? I forgot the mass. So this is 3. This is 0.3 into 10 into 5 minus 4. So this is 15, 1.5, 15, and 15 minus 4 is 11 joules. Okay, so that's the kinetic energy at the bottom. Again, many ways to calculate it, but this is the best way to calculate it because we are doing this chapter. I don't want to miss an opportunity to use all of this concept. A very good question. And yeah, you can pause and have a look.